The size of a fireplace log, this bundle of nuclear fuel generates a lot more heat and is packed with enough uranium to power 100 homes for a year. Here in Saskatchewan, Canada, they extract the uranium from a depth of 500 meters below ground. It's one of the largest deposits of high-grade uranium in the world. The uranium ore lies beneath a bed of water-saturated sandstone. To reach it, drill bits with tungsten carbide studs are used to carve through the rock face. First, holes 45 centimeters wide and spaced 2 meters apart are drilled to house pipes that will be used to freeze the groundwater surrounding the ore. Equipment operated by remote control is used to transfer a new piece of pipe to the end of the drill every meter and a half as it penetrates 120 meters into the sandstone bed. It takes up to 8 days to install each pipe, with 200 needed to surround the ore deposit. These freeze pipes will stabilize the ground and freeze the highly pressurized groundwater to minimize the risk of the mine flooding. Above ground, a freeze plant chills calcium chloride brine to minus 32 degrees Celsius before sending it through the freeze pipes. The brine absorbs heat from the ground to freeze it before looping back to be chilled again. It can take 6 months to complete the freezing process, after which the ore can finally be mined. The first stage is to drill a 30-centimeter diameter pilot hole in the ore body. This maps out a route to reach the ore and creates an entry point for larger mining equipment. From a raised position, the bit bores vertically into the rock to drill the pilot hole and reach a specific level below the ore body. It's now time to deploy the reamer bit. This drill, 3 meters in diameter, has numerous stud-encrusted rotating heads. A drill positioned above the ore pulls the reamer up through the pilot hole to widen the tunnel. Any broken ore falls down into an extraction chamber. Here, a tram operated by remote control scoops up the rock. This remote control system keeps miners a safe distance from falling rocks and minimizes their exposure to the radioactive uranium in the ore. As a further precaution, the mine is continually ventilated to introduce fresh air every 20 minutes. Steered by the operator's joystick, the tram delivers the ore to a scanner. By measuring the amount of radioactivity in the ore, the scanner determines the uranium content is around 15%. In much of the ore in this mine, the uranium content is even greater, on average around 18%, which is considered to be very high grade. The tram now empties the ore into a chute. Cameras follow the rock's journey to the next station. From a control room, operators then manipulate a hydraulic hammer to further break up the ore. The broken pieces then migrate to a mill that grinds them into a fine sand. The addition of water converts the ore to slurry, which can be pumped to the surface. Trucks then transport the uranium ore slurry to a mill 80 kilometers away. At the offloading facility, a vacuum system aligns precisely with the slurry tank. Once in position, a vacuum pipe drops into the tank and suctions up the slurry. Cameras provide a live feed of the unloading process to a control room 7 meters away, where the technicians can observe the procedure in safety. Once washed and checked for radiation, the truck departs, leaving the uranium ready to be transformed into nuclear fuel. In the next stage of the process, the ore is treated with acid, which dissolves the uranium but not the rest of the rock, which settles to the bottom of the tank. The uranium acid solution is then drawn off, leaving the unwanted minerals behind. A series of chemical reactions now further purifies the uranium. Heating to 850 degrees Celsius then concentrates it into a jet black powder. The uranium powder flows into steel drums. A tap of the lip of the drum removes any residual powder. A press is then used to tightly secure the lid to the drum. And finally, it's sealed with a steel ring. It's then labelled to indicate its contents, weight and radioactivity. Stacked in a warehouse, the drums await shipment to the next processing plant. Here, the uranium is transformed from black to yellow as it's converted to uranium trioxide, an interim chemical form in the processing chain. The uranium trioxide is transported in specially designed hoppers. Upon arrival at the next facility, a valve opens at the bottom and the powder flows into conveyor tubes that take it into the plant. Inside, the uranium trioxide powder is dissolved in acid. A sample is tested to confirm that the density and the chemistry are both acceptable. A chemical is then added to turn the dissolved uranium back into a solid. After further processing, the uranium trioxide becomes uranium dioxide, the chemical form required for nuclear fuel. Tumbling the uranium dioxide mixes the different sized particles to make it a more homogeneous blend. The chemical processing has also caused the uranium to change colour again as it transforms into a fine powder. Using several tons of pressure, tools shape the uranium dioxide into pellets. A revolving wheel guides the pellets into a channel conveyor which deposits them into a furnace. Over 24 hours, the heat removes pores in the pellets, which causes them to shrink and increase in density. As the particles fuse together, the pellet hardens into a ceramic. Here's a pellet before and after baking. A robotic arm now loads the pellets onto a tray and levels them. As the conveyor moves the tray forward, another robot places zirconium fuel tubes on a rack. Zirconium is a metal that's highly resistant to both heat and corrosion, but allows neutrons to pass freely through it during the fission reaction. When the tray of pellets reaches the rack of tubes, a robotic loader pushes a stack of 30 pellets into each tube. Another robot delivers the rods, one at a time, to an automated welder that caps the ends. A total of 37 rods are arranged in an upright position within the fixture. Once the rods have been welded into position and the bundle capped at both ends, a robot transfers it to a scale. This verifies that the correct amount of uranium is in the bundle. Prior to their use in a reactor, the amount of radioactivity emitted by nuclear fuel bundles is very low, and they're safe to handle as they're prepared for shipping. Their next stop will be a nuclear power station. And now you know how it's made. It's time for me, like an atom, to split.